Welcome to the Math 1, Unit 7, Lesson 5 summary video, Lines at the State Fair. This lesson is a develop understanding task, which is meant to introduce you to a concept, but not necessarily finalize rules or strategies. The purpose of this lesson is to develop the idea of the second difference in order to write the general expression for a pattern that is growing quadratically. Waiting in line at the state fair, for better or worse, is part of the experience. As more people join the line, the waiting expands. The set of figures below describes how large the waiting area is in each stage of growth. Each block represents 1 square meter. So the first question asks us to determine what patterns we notice in the set of figures. And so when we look at these, what we can immediately see is that it's growing. And when we look at each step, we can see that as the steps progress, it's growing by 1 row and 1 column each time. So what we want to get out of this lesson is several things, but one of the things that we want to do is we want to think back to the strategies that we used when we were looking at linear and exponential sequences in Unit 1. We were able to represent those sequences with models and tables, graphs, and equations. And so we're going to use those same strategies in this lesson. So if we immediately count up the blocks in each of the steps, this is what we find. And so if we were to graph these points, we would see that it looks like this. So right off the bat, we would start thinking, well, this looks like an exponential function because we see that curved line that we're familiar with from Unit 1. But if we look a little more closely at the differences or ratios, looking for a common difference or a common ratio in our table, we don't see those. So the difference between the first two outputs is 3, between the second and third is 5, between the third and the fourth is 7, and the fourth and the fifth is 9. So there's no common difference, which tells us that it's not a linear function. And we know that there's no common ratio to get from 2 to 5 and 5 to 10, 10 to 17, and 17 to 26. So that tells us that it can't be exponential. So we're going to explore this a little bit more to see if we can figure out what these all have in common. What we do notice, if we look a little more closely at those differences of 3, 5, 7, and 9, is that they all have a common difference. And their common difference is 2. So this is something new that we haven't seen in a previous lesson. And we refer to the first set of differences as the first difference, and the second set of differences as the second difference. And so what we notice again here is that we have a common second difference. So we're asked to try to figure out the pattern or how we could represent the pattern that we're seeing. And there's 3 different ways that I'm going to show you today that we can view these patterns growing. And the first one looks like this. So if we were to take we know that this is the 5th step in our sequence. If we were to take So we're saying n is 5. If we were to take n and add 1 to it, we would get 6. And that is the height of our entire figure. So this is 6. And then if we were to take our n, 5, and subtract 1 from that, that gives us the width of this center, the 4 center columns. And so that would give us the area of this entire center piece. And then we have the +2, which represent these extra 2 pieces here and here. And so if we were to substitute that 5 in the expression here, then we would see that we would have the 5 plus 1 and the 5 minus 1 plus 2. The 5 plus 1 would give us 6. The 5 minus 1 would give us 4. And then if we add the 2, we would get 24 plus 2, or 26. And if we look back over to our table of values from the previous slide, that matches what we found when we counted up all of the blocks. So here's another way that some students may view this. In this one, it's saying, again, if we were on our 5th step, and so n would equal 5. And it's saying if we take 1 away from the current step that we're on, that would give us 4. And that gives us this center height right here. And then if we do that again, we start with the 5 and we take away 1. That gives us another 4, which gives us this width here. And so that together is giving us the length and the width, or the area of this center piece, all in here. So all of this. And then it's saying take the current step, n, and double that. That's the 2n. And so that is represented here. So it's saying that we have 5 units here, and we have 5 more units here, and we're on our 5th step. So it's saying take the step number that you're on, 5, and double it. And so we can see that another way that we could look at this is, instead of saying n minus 1 times n minus 1, we know that when we multiply something by itself, that's the same as squaring it. So we could rewrite this as n minus 1 squared plus 2n. These are equivalent. And so if we substitute the 5 into this initial expression, we would get 5 minus 1 is 4, times 5 minus 1 is 4, plus 2 times 5. So we'd end up with 16 plus 10, or 26, which again matches what we found in our table and matches what we found if we looked at it the first way we described. So then if we look at the last way, this is saying n times n plus 1. Again, we're on the 5th step, so our n is 5. And so this is saying we're going to take these initial 5 pieces on the bottom, and we're going to kind of cancel these out because we're going to move them. So we're going to take them off of the bottom, and then we're going to recreate them over here. So we're going to just flip those around over here and add them to the left side of our figure. And so they're no longer down here. We've taken them all and moved them over here. And so now we have a square that is 5 units by 5 units and that's what the n times n represents. And so that's all of this in here, plus our one extra unit, which is this one extra square here. And we, again, know that when we multiply something by itself, it's the same as squaring it, so we could also write this expression as n squared plus 1. When we substitute our 5 in, we get 5 times 5 is 25, plus 1 is 26, and again, that matches what we have here. So are all of these expressions equivalent? Well, if we look at the first one and we distribute, we talked about this in the last lesson, if we distribute that first n to each of the terms in the second binomial, and then the 1 to each of the terms in the second binomial, and then we simplify by combining these like terms, we end up with n squared minus 1n plus 1n, those equal 0, minus 1 plus 2, that equals 1. So this expression simplifies down to this. And when we look at the second expression, we're going to do the same thing. We're going to distribute that n to each of the terms in the second binomial, distribute the 1 to each of the terms in the second binomial, and then add the 2n. When we simplify, here we've got n squared minus 1n minus 1 more n, that equals negative 2n, plus these 2n equals 0, and we're left with the plus 1, so n squared plus 1. And we can see that this expression is equivalent to this expression because when we simplify these, we simplify down to the same binomial. And then finally, in the last example, n times n is n squared plus 1. And again, we can see that all three of these expressions simplify down to the same binomial. Additionally, we can think back to the previous slide where we substituted in the 5 into each of these original expressions, and we ended up with the same value of 26.